What if everything we thought we knew about black holes was just the tip of the cosmic iceberg? These mysterious giants of the universe, where gravity is so intense that not even light can escape, have long fascinated scientists and dreamers alike. But what if black holes aren't just cosmic vacuum cleaners? What if there's something far more extraordinary, portals to other universes? Today, we're diving into the mind-bending idea that black holes could be gateways to realms beyond our own. From the groundbreaking theories of Einstein to the latest discoveries in astrophysics, we'll explore the tantalizing possibility that these cosmic enigmas might hold the key to unlocking the secrets of the multiverse. So, buckle up. This journey will take you to the very edge of what we understand about space, time, and reality itself. Are you ready to question everything you thought you knew? Let's begin. To truly grasp the awe-inspiring nature of black holes, we need to take a step back and explore what they are at their core. Picture a star, a colossal ball of gas burning brightly for millions, even billions of years. But when a star much larger than our Sun exhausts its fuel, it doesn't just fade away. It collapses under its own immense gravity, compressing into a point so dense that it warps the very fabric of space and time. This is the birth of a black hole, a region where gravity becomes so overpowering that it creates a one-way exit for anything that crosses its boundary, known as the event horizon. Once something passes this point, there's no turning back. Not even light, the fastest thing in the universe, can escape its pull. But black holes aren't just destructive forces, they're also cosmic mysteries that challenge our understanding of physics. At their center lies a singularity, a point where the laws of physics as we know them break down. Here, matter is crushed into infinite density, and space and time cease to behave in ways we can comprehend. It's as if the universe itself is holding its breath, waiting for us to unlock its secrets. And yet, black holes aren't entirely invisible. While we can't see them directly, we can observe their effects. Imagine a black hole as a cosmic whirlpool, pulling in gas, dust, and even entire stars. As this material spirals inward, it heats up to incredible temperatures, emitting radiation that we can detect. These glowing rings of light, called accretion disks, are like cosmic breadcrumbs guiding scientists to the black hole's location. Black holes also come in different sizes, from stellar mass black holes, which are a few times more massive than our Sun, to supermassive black holes, which can weigh billions of times as much. These supermassive giants often sit at the center of galaxies, including our own Milky Way, acting as gravitational anchors that shape the cosmos around them. So, while black holes might seem like the ultimate cosmic dead ends, they're anything but. They're gateways to new questions, new discoveries, and perhaps even new realities. And as we continue to study them, we're not just learning about the universe, we're learning about the very nature of existence itself. The event horizon, it's a term that sounds almost poetic, but its implications are anything but gentle. This invisible boundary marks the ultimate point of no return, the moment when the gravitational pull of a black hole becomes so overwhelming that nothing, not even light, can break free. Imagine standing at the edge of a vast, bottomless pit, feeling the ground crumble beneath your feet as you're pulled into the abyss. That's the event horizon, a one-way ticket into the unknown. But what exactly happens as you cross this threshold? According to Einstein's theory of relativity, space and time behave in ways that defy our everyday experience. As you approach the event horizon, time begins to slow down, a phenomenon known as time dilation. To an outside observer, it might seem like you're frozen in place, your movements gradually grinding to a halt. Yet, from your perspective, time would feel normal, even as the universe around you speeds up. It's a mind-bending paradox that challenges our understanding of reality itself. And then there's the distortion of space. As you near the event horizon, the fabric of space becomes stretched and warped, like a rubber sheet pulled taut by an immense weight. Light bends around the black hole, creating strange visual effects. If you could peer out from just outside the event horizon, you'd see the universe twisted and distorted, as if looking through a cosmic funhouse mirror. But what lies beyond this boundary, that's where things get truly fascinating. Some theories suggest the event horizon isn't just a dead end, it could be a gateway. A passage to another realm, another universe, or perhaps even another point in time. While we can't yet prove this, the idea sparks the imagination. What if crossing the event horizon doesn't mean destruction but transformation? What if it's the beginning of a journey into uncharted territory where the rules of physics as we know them no longer apply? Of course, these ideas are still speculative, but they're grounded in real science. The event horizon isn't just a boundary, it's a frontier. It's a place where the known meets the unknown, where the laws of physics are pushed to their limits. And as we continue to study black holes, we're not just exploring the cosmos, we're exploring the very edges of what it means to exist. So, the next time you hear about the event horizon, don't just think of it as a cosmic trap. Think of it as a puzzle, a mystery waiting to be solved. Who knows, the answers we find might just change the way we see the universe and our place within it. At the very heart of a black hole lies its most enigmatic feature, the singularity. This is the point where all the laws of physics as we know them cease to make sense. Imagine compressing an entire star, or even billions of stars, into a single point of infinite density. The gravitational force here becomes so intense that it warps space and time beyond recognition, creating a region where the universe itself seems to hold its breath, waiting for answers we have yet to uncover. But what exactly is a singularity? In simple terms, it's a place where the rules of physics break down. Gravity becomes infinite, and space-time curves so drastically that our current understanding of reality no longer applies. It's as if the universe has drawn a curtain here, hiding its deepest secrets from us. For decades, scientists have grappled with this concept, trying to reconcile it with the equations of general relativity and quantum mechanics. Yet, the singularity remains one of the greatest mysteries in astrophysics. Now, here's where things get even more intriguing. Some theorists propose that singularities might not be dead ends, but rather bridges, portals to other universes or entirely different regions of space-time. Picture a cosmic tunnel where the extreme conditions at the singularity could tear a hole in the fabric of our reality, opening a doorway to another. This idea, while speculative, is rooted in the mathematics of relativity and quantum physics. It suggests that singularities could be the ultimate cosmic crossroads, connecting our universe to realms beyond our imagination. But before we get too carried away, let's consider the challenges. First, the conditions near a singularity are so extreme that any object, or even information approaching it, would be torn apart by tidal forces long before reaching the center. The idea of surviving such a journey seems impossible with our current understanding of physics. Second, even if a singularity could serve as a gateway, we have no way of knowing what lies on the other side. Would it lead to another universe, a parallel dimension, or something entirely beyond our comprehension? Despite these obstacles, the concept of singularities as interuniversal portals continues to captivate scientists and dreamers alike. It forces us to rethink the nature of space, time, and reality itself. Could these cosmic anomalies be the key to unlocking the multiverse, or are they simply reminders of how much we still have to learn about the universe? As we peer into the heart of a black hole, we're not just exploring the limits of science, we're pushing the boundaries of human curiosity. The singularity, with all its mystery and paradox, invites us to dream bigger, to question deeper, and to imagine the unimaginable. And who knows, the answers we find might just redefine our place in the cosmos. Now, let's shift our focus to one of the most tantalizing ideas in modern physics, wormholes. Often referred to as Einstein-Rosen bridges, these hypothetical tunnels through space-time have captured the imagination of scientists and science fiction fans alike. Picture a cosmic shortcut, a tunnel that bends the fabric of the universe, connecting two distant points in an instant. It's like folding a piece of paper so that two far apart dots touch, creating a bridge where none existed before. But could these wormholes actually exist? And if so, could black holes be the key to finding them? The concept of wormholes emerges directly from Einstein's theory of general relativity. According to the equations, these tunnels could form under extreme conditions, creating a passage through space-time that links two separate regions. In theory, a wormhole could connect not just distant parts of our universe, but even entirely different universes. It's a mind-boggling idea, but one that's grounded in the same math that describes black holes and the curvature of space-time. But here's the catch: while wormholes are mathematically possible, we've never observed one. They exist in the realm of theory, not yet in reality. The challenge lies in their instability. According to current understanding, a wormhole would require exotic matter, something with negative energy, to keep it open and stable. Without this, the tunnel would collapse almost instantly, making it impossible to traverse. This is where black holes come into the picture. Some scientists speculate that black holes could serve as the entrances to wormholes. Imagine a black hole as one end of a cosmic tunnel, with the other end leading to a distant region of space, or perhaps even another universe entirely. The immense gravitational forces of a black hole might create the conditions necessary for such a tunnel to form. But before we get too excited, there's a major hurdle. Crossing a black hole to reach a wormhole would be no easy feat. The tidal forces near a black hole's event horizon are so extreme that they would tear apart anything or anyone long before it could reach the hypothetical tunnel. Still, the idea of wormholes as cosmic shortcuts raises fascinating questions. What if we could harness these tunnels for interuniversal travel? What if they're the missing link between our universe and others in the multiverse? While these possibilities remain speculative, they push the boundaries of our understanding and inspire us to explore the unknown. Wormholes remind us that the universe is full of mysteries waiting to be solved. They challenge us to think beyond the limits of our current knowledge and imagine a cosmos where the impossible might just be possible. And as we continue to study black holes and the fabric of space-time, we're not just seeking answers, we're embarking on a journey to uncover the very nature of reality itself. At the heart of every black hole lies not just a singularity, but a profound challenge to our understanding of physics, especially when we bring quantum mechanics into the picture. While Einstein's theory of general relativity paints black holes as regions where space and time collapse, quantum mechanics tells a different story. At the quantum level, the universe operates by rules that seem almost magical compared to the predictable nature of classical physics. Particles can exist in multiple places at once, information can be entangled across vast distances, and nothing is ever truly lost. This raises a fascinating question. What happens when the strange world of quantum mechanics meets the extreme environment of a black hole? One of the most puzzling aspects of black holes is the so-called information paradox. According to classical physics, anything that crosses the event horizon is lost forever, including the information it carries. But quantum mechanics suggests that information can never truly be destroyed. It's always preserved, even if it's scrambled beyond recognition. This contradiction has left scientists scratching their heads for decades. How can a black hole, which seemingly devours everything, also preserve information in some form? Some theories propose that black holes might encode information in their event horizons, storing it like a cosmic hard drive. Imagine the surface of a black hole as a hologram, where every bit of information about the objects that fell in is etched onto its boundary. This idea, known as the holographic principle, suggests that the information isn't lost, it's just transformed into a form we don't yet fully understand. It's as if the black hole is a cosmic librarian, meticulously cataloging every detail of its contents in a language we're still learning to decode. But the quantum mysteries don't stop there. Some researchers believe that quantum entanglement, a phenomenon where particles remain connected across vast distances, could play a key role in black hole dynamics. If particles falling into a black hole remain entangled with those outside, it's possible that information could escape in subtle ways, defying the classical notion that nothing can leave a black hole. This could mean that black holes aren't just cosmic dead ends, but intricate systems that process and transmit information in ways we're only beginning to grasp. And then there's the tantalizing idea that black holes might serve as quantum gateways. If quantum mechanics allows for the preservation of information, could it also enable travel between universes? Some speculative theories suggest that the extreme conditions inside a black hole might create quantum tunnels, short-lived connections to other regions of space-time, or even entirely different universes. While this remains firmly in the realm of theory, it's a concept that pushes the boundaries of what we thought was possible. Quantum mechanics doesn't just complicate our understanding of black holes, it enriches it. By introducing concepts like superposition, entanglement, and information preservation, it forces us to rethink the very nature of these cosmic phenomena. Black holes are no longer just gravitational monsters, they're laboratories for exploring the deepest mysteries of the universe. And as we continue to unravel the quantum secrets hidden within them, we might just find answers that reshape our understanding of reality itself. So, while the marriage of quantum mechanics and black holes may seem like a paradox, it's also a source of endless fascination. It challenges us to think beyond the limits of classical physics and imagine a universe where the rules are far stranger and far more exciting than we ever imagined. And who knows, the answers we find might not just explain black holes, they might reveal the very fabric of the cosmos. For decades, black holes were thought to be the ultimate cosmic vacuums, places where nothing, not even light, could escape. But in the 1970s, physicist Stephen Hawking turned this idea on its head with a groundbreaking discovery. He proposed that black holes aren't completely black after all. Instead, they emit a faint glow of radiation, now famously known as Hawking radiation. This revelation didn't just challenge our understanding of black holes, it opened the door to a whole new realm of possibilities. So, how does Hawking radiation work? It all comes down to the strange behavior of quantum particles near the event horizon. In the vacuum of space, particles and their antiparticles constantly pop into existence, only to annihilate each other almost instantly. But at the edge of a black hole, something extraordinary happens. If one of these particles falls into the black hole while the other escapes, the black hole loses a tiny amount of energy. Over time, this process causes the black hole to slowly evaporate. It's as if the black hole is leaking energy, one particle at a time, but here's where it gets even more intriguing. Hawking radiation isn't just random energy, it's thought to carry information. That's right, the very particles escaping the black hole might hold clues about what's inside. This idea has sparked intense debate among scientists. If information can escape a black hole, does that mean the event horizon isn't the impenetrable barrier we once thought? Could this radiation be a window into the mysteries lurking beyond? Some researchers believe Hawking radiation could offer hints about the nature of singularities or even the existence of other universes. Imagine if the particles emitted by a black hole carried encoded messages, tiny fragments of data about the objects that fell in. While we're still far from decoding this cosmic cipher, the possibility is tantalizing. It suggests that black holes might not be the ultimate dead ends we once believed them to be. Of course, detecting Hawking radiation is no easy task. It's incredibly faint, dwarfed by the cosmic background radiation that fills the universe, but scientists are working on innovative ways to observe it, from advanced telescopes to experiments that simulate black hole conditions in labs. If we could capture and analyze this radiation, it might provide unprecedented insights into the inner workings of black holes, and perhaps even reveal whether they serve as gateways to other realms. Hawking radiation reminds us that the universe is full of surprises. What we once thought were inescapable voids might actually be dynamic, ever-changing entities. They challenge us to rethink the boundaries of space, time, and information itself. And as we continue to explore these cosmic enigmas, we're not just uncovering the secrets of black holes, we're rewriting the story of the universe itself. So the next time you hear about Hawking radiation, think of it as more than just a scientific curiosity. It's a beacon of hope, a faint signal from the depths of a black hole that whispers, there's more to discover. And who knows, the answers we find might just change everything we thought we knew about the cosmos. One of the most profound challenges in modern physics lies at the intersection of black holes and quantum mechanics, a puzzle so baffling it's known as the information paradox. At its core, this paradox forces us to confront a fundamental question. Can information truly disappear, or is it always preserved, even in the most extreme environments? On one hand, quantum mechanics tells us that information can never be destroyed. It can only change form. On the other, black holes seem to obliterate everything that crosses their event horizons, leaving no trace behind. How do we reconcile these two seemingly contradictory ideas? Let's break it down. In the quantum world, every particle, every atom, every bit of energy carries information. This information is like a cosmic fingerprint, unique and irreplaceable. Even when particles interact or change, their information is conserved. It's a principle so fundamental that it underpins much of our understanding of the universe. But black holes, with their immense gravitational pull, appear to violate this rule. When something falls into a black hole, it's gone, seemingly erased from existence. This contradiction has led scientists to propose some truly mind-bending solutions. One idea is that the information isn't lost, it's encoded on the surface of the black hole's event horizon. Think of it like a hologram where every bit of data about the objects that fell in is imprinted on the boundary. This concept, known as the holographic principle, suggests that the event horizon acts as a kind of cosmic hard drive, storing information in a way we don't yet fully understand. Another theory involves quantum entanglement, a phenomenon where particles remain connected across vast distances. If particles falling into a black hole remain entangled with those outside, it's possible that information could escape in subtle, unexpected ways. This could mean that black holes aren't the ultimate cosmic shredders we once thought. They might be processing and transmitting information in ways we're only beginning to grasp. Then there's the tantalizing possibility that the information paradox could hint at something even grander, the existence of other universes. If information isn't destroyed but instead transferred, could it be escaping into another realm entirely? Some speculative theories suggest that black holes might be portals funneling information, and perhaps even matter, into parallel dimensions or alternate realities. While this remains firmly in the realm of theory, it's a concept that pushes the boundaries of what we thought was possible. Resolving the information paradox isn't just an academic exercise, it could fundamentally change our understanding of the universe. If we can figure out how black holes handle information, we might unlock deeper truths about the nature of reality itself. Are black holes cosmic dead ends, or are they gateways to something far more extraordinary? As we grapple with this paradox, we're reminded that the universe is far stranger and more complex than we can imagine. It challenges us to think beyond the limits of our current knowledge and explore the unknown. And while we don't yet have all the answers, the journey to uncover them is just as thrilling as the destination. So, the next time you ponder the mysteries of black holes, remember, the information paradox isn't just a problem to solve, it's an invitation to dream bigger and explore deeper than ever before. As we continue our journey into the mysteries of black holes, let's take a moment to consider an even grander possibility, the multiverse. This idea, which has captivated scientists and science fiction writers alike, suggests that our universe might not be the only one. Instead, it could be just one of countless universes, each with its own unique set of physical laws, constants, and even dimensions. Imagine a cosmic tapestry woven with infinite threads, each representing a universe with its own story to tell. Now here's the twist. If black holes truly are gateways, could they be the bridges that connect us to these alternate realities? The multiverse theory isn't just a flight of fancy, it's rooted in serious scientific inquiry. Some versions of the theory arise from quantum mechanics, where every possible outcome of an event creates a branching universe. Others stem from cosmic inflation, the rapid expansion of the early universe, which could have spawned bubble universes, each with its own distinct properties. And then there's string theory, which proposes that our universe is just one of many embedded in a higher dimensional space. These ideas, while still speculative, offer a compelling framework for understanding the vastness of existence. So, where do black holes fit into this picture? If black holes are indeed portals, they could serve as the cosmic doorways between these universes. Picture a black hole as a kind of interdimensional tunnel, where the extreme conditions at the singularity might create a rupture in the fabric of space-time, linking our universe to another. It's a concept that pushes the boundaries of our imagination, suggesting that black holes aren't just destructive forces but potential connectors to realms beyond our own. But how plausible is this idea? While the math supporting the multiverse is intriguing, it's important to note that we have no direct evidence, yet black holes, with their intense gravitational fields and mysterious interiors, are the perfect candidates for such a role, but proving it is another matter. The sheer complexity of these cosmic phenomena makes them both a challenge and an opportunity for scientists. Could the singularity at the heart of a black hole be the key to unlocking the multiverse? Or are we simply projecting our hopes onto the unknown? Even if black holes aren't gateways to other universes, the multiverse theory still offers a profound perspective on the cosmos. It reminds us that our universe might be just one chapter in an infinitely larger story. And as we continue to study black holes, we're not just exploring the mysteries of our own universe, we're peering into the possibilities of countless others. The idea of a multiverse invites us to dream bigger, to imagine a cosmos far more vast and diverse than we ever thought possible. It challenges us to rethink our place in the grand scheme of things and to consider that the universe or universes might hold secrets beyond our wildest dreams. So the next time you gaze at the night sky, remember, what we see might just be the beginning of an infinite cosmic journey, one that black holes could help us navigate. And who knows, the answers we find might just redefine everything we thought we knew about reality itself. What if the entire universe could be described as a hologram, a two-dimensional surface encoding all the information of a three-dimensional space? This might sound like science fiction, but it's a serious scientific idea known as the holographic principle. And when we apply this principle to black holes, it opens up a fascinating new way of thinking about how they might function and whether they could serve as gateways to other universes. At its core, the holographic principle suggests that the information contained within a volume of space can be fully represented on its boundary. Think of it like a holographic sticker, a flat surface that, when illuminated, creates the illusion of depth. Similarly, the holographic principle proposes that the surface of a black hole's event horizon, its boundary, could encode all the information about the objects that have fallen inside. It's as if the black hole stores the blueprint of everything it consumes, not within its depths but on its outer edge. This idea has profound implications for how we understand black holes. If the event horizon acts like a cosmic hard drive, preserving information in a holographic form, it challenges the notion that black holes are purely destructive. Instead, they might be incredibly sophisticated information processors, encoding and perhaps even transmitting data in ways we don't yet fully understand. But how could this relate to the idea of black holes as interuniversal portals? Some theorists speculate that the holographic principle might offer a clue. If the event horizon encodes information in a two-dimensional form, it's possible that this data could be projected or decoded elsewhere, perhaps into another universe. Imagine the event horizon as a kind of cosmic projector, beaming information across the fabric of space-time to another location. This could mean that black holes aren't just endpoints, they're conduits transferring information and possibly matter to other realms. Of course, this is still a speculative idea, but it's grounded in some of the most cutting-edge theories in physics. The holographic principle has already revolutionized our understanding of black holes, helping us reconcile the apparent loss of information with the laws of quantum mechanics. It suggests that black holes are far more complex than we once thought, acting not just as cosmic vacuums but as intricate systems that process and preserve information in ways we're only beginning to grasp. So, what does this mean for the possibility of black holes as interuniversal portals? If the holographic principle holds true, it could mean that black holes are more than just gateways, they're cosmic translators, encoding and projecting information across the boundaries of space and time. It's a concept that pushes the limits of our imagination, suggesting that the universe might be far more interconnected than we ever realized. As we explore the holographic principle, we're not just uncovering the secrets of black holes, we're redefining our understanding of reality itself. It's a reminder that the universe is full of surprises waiting for us to uncover them. And who knows, the answers we find might just reveal a cosmos far more extraordinary and far more connected than we ever dreamed possible. What if the event horizon of a black hole isn't just a boundary, it's a wall of fire? This startling idea, known as the Firewall Paradox, has sparked heated debate among physicists and fundamentally challenges our understanding of black holes. Imagine approaching the edge of a black hole, expecting to cross the event horizon and venture into the unknown, only to be met with an inferno of unimaginable energy. This concept doesn't just raise questions, it upends the very framework of how we think about black holes and their potential as gateways to other realms. The Firewall Paradox emerged as a response to a deep conflict between two of physics' most fundamental theories, general relativity and quantum mechanics. According to Einstein's theory, crossing the event horizon should be uneventful, a smooth passage into the black hole's interior. But quantum mechanics tells a different story. As particles near the event horizon, quantum effects could create a searing wall of energy, annihilating anything that comes into contact with it. This fiery barrier contradicts the classical view of black holes and forces us to reconsider what really happens at their boundaries. So, why does this paradox matter? If firewalls exist, they could completely rewrite the rules of black holes as we know them. Instead of being cosmic gateways, black holes might become cosmic incinerators, destroying everything that approaches them. This would make the idea of using black holes for interuniversal travel or even surviving the journey seem impossible. But not everyone agrees. Some physicists argue that firewalls might not exist at all, or that they could be a sign that our understanding of quantum mechanics is incomplete. The debate over firewalls is more than just an academic exercise. It's a clash of ideas that could reshape our understanding of the universe. On one side, proponents of the firewall theory argue that it's the only way to resolve the information paradox, ensuring that information isn't lost when it enters a black hole. On the other side, skeptics believe that firewalls violate the principles of general relativity, which predict that crossing the event horizon should be a smooth, uneventful process. One intriguing possibility is that both sides might be right in a way. Some theories suggest that firewalls could form under specific conditions, but they might not be a universal feature of all black holes. For example, smaller black holes or those with certain properties might not produce firewalls, leaving the door open literally for the possibility of interuniversal travel. The Firewall Paradox reminds us that black holes are far more mysterious than we once thought. They're not just gravitational giants or cosmic gateways, they're laboratories for testing the most extreme ideas in physics. Whether firewalls exist or not, the debate pushes us to explore deeper, question harder, and imagine a universe that's far stranger and far more fascinating than we ever dreamed. As we grapple with this paradox, we're reminded that the universe is full of surprises, waiting for us to uncover them. And while we don't yet have all the answers, the journey to find them is just as thrilling as the destination. So, the next time you think about black holes, remember, the Firewall Paradox isn't just a problem to solve, it's an invitation to explore the very edges of what we know and to dream of what lies beyond. While black holes captivate us with their immense gravitational pull and mysterious interiors, there's another cosmic enigma that might hold the key to understanding them even further: dark matter and dark energy. Together, these invisible forces make up an astonishing 95% of the universe, yet we still know very little about what they actually are. Dark matter, which doesn't emit or reflect light, binds galaxies together with its gravitational influence, while dark energy drives the accelerating expansion of the universe. But what if these shadowy forces aren't just cosmic background players? What if they're intricately connected to the behavior of black holes and their potential to serve as gateways to other universes? Let's start with dark matter. This elusive substance doesn't interact with light, making it invisible to our telescopes, but its gravitational effects are unmistakable. Galaxies rotate faster than they should based on the visible matter alone, and galaxy clusters hold together in ways that defy conventional physics. Now, imagine black holes as cosmic hubs where dark matter might accumulate. Could this invisible matter influence the way black holes form or behave? Some theories suggest that dark matter could even alter the structure of a black hole's event horizon, potentially creating conditions that make interuniversal travel more plausible. But dark matter isn't the only piece of the puzzle. Dark energy, the mysterious force causing the universe to expand at an accelerating rate, might also play a role. While it's often thought of as a repulsive force acting on the largest scales, its effects on black holes are less understood. Could dark energy's influence stretch the fabric of space-time near a black hole in ways that open pathways to other universes? The idea is speculative, but it's an intriguing possibility. If dark energy can push the universe apart, perhaps it could also create the conditions needed for black holes to function as cosmic bridges. Now, let's consider how these forces might work together. Dark matter's gravitational pull could shape the environment around a black hole, while dark energy's expansive force might counteract it, creating a delicate balance. This interplay could be the key to unlocking the mysteries of black holes as interuniversal portals. Picture a black hole surrounded by a dense halo of dark matter, with dark energy subtly warping space-time around it. Could this combination create the perfect conditions for a gateway to another universe? Of course, these ideas are still in the realm of theory. We don't yet have the tools to directly observe dark matter or fully understand dark energy, let alone how they interact with black holes. But that's what makes this field so exciting. Every unanswered question is an opportunity to push the boundaries of our knowledge and imagine new possibilities. As we continue to study these mysterious forces, we might uncover clues that reveal not just the nature of black holes, but the very fabric of the multiverse itself. So, while dark matter and dark energy remain shrouded in mystery, they remind us that the universe is far more complex and far more interconnected than we ever imagined. They challenge us to think beyond what we can see and explore the invisible forces that shape our cosmos. And as we do, we might just find that black holes aren't the only gateways to other realms. They're part of a much larger cosmic tapestry, woven together by forces we're only beginning to understand. The mathematics of black holes is where the rubber meets the road in our quest to understand whether these cosmic giants could serve as interuniversal portals. At the heart of this exploration are two of physics' most profound theories, Einstein's general relativity and quantum mechanics. These frameworks have reshaped our understanding of the universe, but when it comes to black holes, they often seem to speak different languages. So, how do we reconcile these theories, and what do they tell us about the possibility of black holes as gateways to other realms? Let's start with general relativity, Einstein's masterpiece. This theory describes gravity not as a force, but as the curvature of space-time caused by mass and energy. Black holes, with their immense gravitational pull, are extreme manifestations of this curvature. The equations of general relativity predict that at the center of a black hole lies a singularity, a point where density becomes infinite and space-time breaks down. It's here that the math takes us to the edge of what we can comprehend, hinting at phenomena beyond our current understanding. But general relativity alone doesn't tell the whole story. When we zoom into the quantum level, the rules change. Quantum mechanics governs the behavior of particles at the smallest scales, and its principles often clash with the smooth, continuous space-time described by Einstein. For instance, quantum mechanics suggests that particles can pop in and out of existence, and that information can never truly be lost. Ideas that seem at odds with the classical view of black holes as cosmic vacuum cleaners. This tension between the two theories is where things get truly fascinating. Some physicists have proposed that black holes might be the key to unifying general relativity and quantum mechanics, offering a glimpse into a deeper, more fundamental understanding of the universe. One such idea is the concept of quantum tunneling, where particles can tunnel through barriers that would be insurmountable under classical physics. Could this phenomenon occur on a cosmic scale, allowing matter or energy to traverse a black hole and emerge in another universe? Mathematical models supporting this idea do exist, but they're highly speculative. For example, some solutions to Einstein's equations suggest the existence of wormholes, hypothetical tunnels through space-time that could connect distant regions of the universe or even different universes entirely. These models rely on exotic forms of matter with negative energy, which have yet to be observed. Still, the math shows that such structures are theoretically possible, even if they remain beyond our current ability to detect or create. Another intriguing possibility comes from string theory, which attempts to reconcile general relativity and quantum mechanics by proposing that the fundamental building blocks of the universe are tiny, vibrating strings. In this framework, black holes could be seen as brains, multidimensional surfaces that interact in ways we're only beginning to understand. Some string theorists suggest that black holes might serve as bridges between these branes, offering a mathematical pathway to other universes. Of course, these ideas are far from proven. The mathematics of black holes is incredibly complex, and many of the models describing them rely on assumptions or conditions that we can't yet test. But that's what makes this field so exciting. Every equation, every model, every theoretical framework brings us one step closer to understanding whether black holes could truly be cosmic gateways. As we delve into the mathematics of black holes, we're reminded that the universe is a puzzle waiting to be solved. The equations of general relativity and quantum mechanics are the tools we use to decode its secrets, and black holes are the ultimate test of our ingenuity. Whether or not they serve as portals to other realms, the journey to understand them is a testament to the power of human curiosity and the boundless possibilities of the cosmos. So, as we continue to explore the mathematics of black holes, let's keep an open mind. The answers we find might not just explain these cosmic enigmas, they could redefine our understanding of reality itself. Time dilation, one of the most mind-bending effects of Einstein's theory of relativity, takes on a whole new level of strangeness near a black hole. Imagine standing just outside the event horizon, watching the universe around you while time seems to stretch and warp. To an observer far away, your movements would appear to slow down, almost as if you were frozen in place. But from your perspective, time would feel normal, even as the rest of the universe races ahead. This isn't just a quirky thought experiment. It's a real phenomenon with profound implications for how we think about space, time, and the possibility of interuniversal travel. At its core, time dilation occurs because gravity warps the fabric of space-time. The stronger the gravitational field, the more time slows down. Near a black hole where gravity is at its most extreme, this effect becomes dramatic. For someone hovering close to the event horizon, minutes could pass while years or even centuries elapse for those far away. It's like stepping into a cosmic time machine where the flow of time itself becomes malleable. Now, let's take this idea a step further. If time dilation can slow time to such an extreme degree, could it also enable journeys between universes? Picture this: as you approach a black hole, time slows down so much that what feels like a few moments to you could equate to millennia in another part of the universe, or even in another universe entirely. This means that, in theory, you could traverse vast cosmic distances in what seems like an instant from your perspective. To an outside observer, it might look like you vanished, only to reappear in a completely different realm. But how does this work in practice? One possibility is that time dilation could act as a kind of cosmic shortcut. By exploiting the extreme warping of time near a black hole, a traveler could effectively skip large swaths of space-time, emerging in a distant region, or even another universe without experiencing the passage of time as we normally understand it. It's a concept that pushes the boundaries of our imagination, suggesting that black holes might not just bend space, but also time itself. Of course, there are challenges to this idea. For one, surviving the journey would require overcoming the immense gravitational forces near a black hole, which could tear apart anything or anyone long before they reach the event horizon. Additionally, we still don't fully understand how time dilation interacts with other phenomena, like quantum mechanics or the nature of singularities. Could time dilation create a stable pathway to another universe, or would it simply trap travelers in an endless loop of stretched-out time? Despite these uncertainties, the idea of using time dilation for interuniversal travel is a tantalizing one. It forces us to rethink the nature of time and space, and to consider that the universe might be far more interconnected and far more flexible than we ever imagined. Time dilation isn't just a quirk of physics. It's a reminder that the cosmos is full of possibilities, waiting for us to explore them. So, as we ponder the role of time dilation in black holes, let's keep an open mind. The answers we find might not just explain the mysteries of these cosmic giants, they could redefine how we think about time, travel, and the very fabric of reality itself. And who knows, the journey to uncover these secrets might just take us places we never thought possible. Beyond the event horizon lies another fascinating feature of rotating black holes, the ergosphere. This region, shaped like a flattened sphere surrounding the black hole, is where space-time itself is dragged along by the black hole's immense spin. Imagine a whirlpool in space where the very fabric of reality is twisted and pulled in a cosmic dance. Unlike the event horizon, which is a one-way boundary, the ergosphere offers a unique opportunity, a place where energy can be extracted and perhaps where the secrets of interuniversal travel could be unlocked. The key to understanding the ergosphere lies in its rotation. As a black hole spins, it drags space-time around with it, a phenomenon known as frame dragging. This creates a region where nothing can stand still, not even light. Any object entering the ergosphere is forced to move in the same direction as the black hole's rotation, like a leaf caught in a swirling river. But here's where it gets truly intriguing. Within this region, the rotational energy of the black hole becomes accessible. This energy isn't just theoretical, it's something we could potentially harness. In the 1970s, physicist Roger Penrose proposed a mechanism, now known as the Penrose process, that could extract energy from the ergosphere. Here's how it works. Imagine sending a particle into the ergosphere and splitting it in two. If one fragment falls into the black hole while the other escapes, the escaping fragment could carry away more energy than the original particle had. It's like taking a loan from the black hole's rotation, using its immense power to fuel something extraordinary. But what does this mean for interuniversal travel? If we could tap into the energy of the ergosphere, it might provide the immense power needed to create or sustain a gateway to another universe. Think of it as a cosmic power plant, capable of generating the energy required to bend space-time on an unimaginable scale. The ergosphere's unique properties could act as a catalyst, transforming the theoretical possibilities of wormholes or other cosmic shortcuts into something tangible. Of course, the challenges are immense. The ergosphere is a region of extreme conditions where the forces at play would test the limits of any technology we could conceive. The intense gravitational tides, the swirling space-time, and the sheer energy required make this a daunting prospect. But it's precisely these challenges that make the ergosphere so captivating. It's a place where the rules of physics are pushed to their limits, and where the potential for discovery is boundless. As we explore the ergosphere, we're reminded that black holes are more than just cosmic curiosities, they're laboratories for the most extreme phenomena in the universe. They challenge us to think beyond the limits of our current understanding and to imagine a future where the impossible might just be possible. Whether or not the ergosphere holds the key to interuniversal travel, it's a testament to the incredible power and mystery of black holes and to the endless possibilities that await us in the cosmos. So, as we continue to unravel the secrets of the ergosphere, let's keep our curiosity alive. The answers we find might not just change how we see black holes, they could revolutionize our understanding of the universe itself. And who knows, the journey to uncover these secrets might just take us places we never thought possible. At the heart of nearly every galaxy lies a supermassive black hole, a cosmic titan millions or even billions of times more massive than the stellar black holes formed from collapsing stars. These giants aren't just larger versions of their smaller counterparts, they're fundamentally different in how they form, behave, and influence their surroundings. But here's the big question. Could these supermassive behemoths serve as more stable or powerful gateways to other universes? Supermassive black holes are unlike anything else in the cosmos. While stellar black holes form from the collapse of massive stars, the origins of their supermassive cousins remain a mystery. Some theories suggest they could have grown from the merging of smaller black holes or from the direct collapse of massive gas clouds in the early universe. Whatever their origins, their sheer size and gravitational influence are staggering. Take Sagittarius A, the supermassive black hole at the center of our Milky Way. With a mass over 4 million times that of our Sun, it dominates the galactic center, shaping the orbits of stars and influencing the structure of our galaxy itself. Now, let's consider their potential as interuniversal portals. One key advantage of supermassive black holes is their size. The larger the black hole, the less extreme the tidal forces near its event horizon. Unlike smaller black holes where the gravitational gradient is so steep that it would tear apart anything approaching, a supermassive black hole's immense size means its tidal forces are spread out over a much larger area. This could make crossing its event horizon, at least in theory, a less destructive experience, but size isn't the only factor. Supermassive black holes often have accretion disks, glowing rings of gas and dust swirling around them at incredible speeds. These disks aren't just cosmic light shows, they're also sources of immense energy. Some scientists speculate that the energy generated by these disks could create the conditions needed for stable wormholes or other cosmic shortcuts. Imagine harnessing the power of a supermassive black hole's accretion disk to open a pathway to another universe. It's a concept that feels straight out of science fiction, but it's grounded in the physics of these extraordinary objects. Another intriguing possibility lies in the role of supermassive black holes in the structure of the universe itself. These cosmic giants are often found at the centers of galaxy clusters, acting as gravitational anchors for hundreds or even thousands of galaxies. If black holes are gateways, could supermassive black holes serve as the ultimate intergalactic hubs, connecting not just individual universes but entire cosmic networks? It's a mind-bending idea, but one that aligns with their central role in the cosmos. Of course, the challenges are immense. We still don't fully understand how supermassive black holes form or how they interact with the fabric of space-time. And even if they could serve as gateways, the energy and technology required to traverse them are far beyond our current capabilities. But that's what makes them so fascinating. Supermassive black holes aren't just cosmic curiosities. They're windows into the most extreme and mysterious aspects of the universe. As we continue to study these galactic giants, we're not just exploring the nature of black holes, we're probing the very foundations of reality. Whether they're gateways to other universes or simply reminders of how much we still have to learn, supermassive black holes invite us to dream bigger and explore deeper than ever before. And who knows, the answers we uncover might just redefine our understanding of the cosmos itself. The idea of traveling through a black hole is the stuff of science fiction, but could it ever become science fact? The challenges are immense, and the dangers are as extreme as anything the universe has to offer. Let's break it down. Even approaching a black hole would be a perilous endeavor. The tidal forces, those immense gravitational pulls that stretch and compress anything in their path, are so powerful near a black hole that they could tear apart stars, planets, or spacecraft long before they reach the event horizon. It's like trying to navigate a ship through a cosmic blender, where every atom is pulled in different directions with unimaginable force, but tidal forces are just the beginning. The radiation near a black hole is another deal breaker. As matter spirals into the black hole, it heats up to incredible temperatures, emitting intense X-rays and gamma rays. These high-energy waves could fry any known material, making it nearly impossible to shield a spacecraft or its occupants. And let's not forget about time dilation. The closer you get to a black hole, the more time slows down relative to the outside universe. While this might sound like a cool way to time travel, It could also mean that by the time you emerge, centuries or even millennia might have passed back home. So is it all doom and gloom? Not necessarily. While the challenges are daunting, they're not necessarily insurmountable, at least not for a civilization far more advanced than ours. Imagine a society that has mastered technologies we can only dream of. Perhaps they've developed materials capable of withstanding the crushing forces of a black hole, or found ways to harness energy from the accretion disk to power their journey. Maybe they've even discovered how to manipulate space-time itself, creating protective bubbles that shield them from the harshest effects of gravity and radiation. One intriguing possibility is the use of quantum technologies. If advanced civilizations have unlocked the secrets of quantum entanglement or quantum shielding, they might be able to teleport information or even matter across vast distances, bypassing the dangers of a black hole altogether. It's a concept that's still in its infancy for us, but for a society thousands or millions of years ahead of us, it might be routine. Of course, these ideas are speculative, and we're nowhere near being able to test them. But that's the beauty of exploring the unknown. It pushes us to think beyond our current limitations and imagine what might be possible. The challenges of surviving a black hole journey are immense, but they're also a reminder of how much we still have to learn about the universe. So, while the idea of traveling through a black hole might seem impossible today, it's worth remembering that the impossible has a way of becoming reality. The technologies we dream of today might one day be the tools that unlock the cosmos. And as we continue to explore, we're not just uncovering the secrets of black holes, we're discovering the potential of what we, as a species, might one day achieve. What if the key to unlocking a black hole's potential as a gateway lies in something we've never even seen? Enter exotic matter, a hypothetical substance that defies the rules of ordinary physics. Unlike the matter we're familiar with, exotic matter possesses negative energy density, meaning it could theoretically create repulsive gravity. This bizarre property makes it a prime candidate for stabilizing wormholes or keeping black hole portals open. But here's the catch: does exotic matter even exist? And if it does, could we ever harness it? To understand why exotic matter is so crucial, let's take a closer look at wormholes. These hypothetical tunnels through space-time are incredibly unstable. Without some form of support, they would collapse almost instantly under their own gravitational pull. That's where exotic matter comes in. Its negative energy density could counteract the immense gravitational forces, propping open the wormhole and making it traversable. It's like using scaffolding to hold up a collapsing tunnel, except this scaffolding is made of something straight out of science fiction. But what exactly is exotic matter? In theory, it's a substance that violates the so-called energy conditions of general relativity, which state that energy density must always be positive. Exotic matter flips this rule on its head, creating a form of energy that pushes rather than pulls. Some physicists believe it might exist in the form of negative mass particles or as a quantum field with unusual properties. While we've never directly observed exotic matter, certain quantum phenomena like the Casimir effect hint at the possibility of negative energy densities in the universe. The Casimir effect, for example, occurs when two uncharged metal plates placed extremely close together create a vacuum energy between them. This energy can be interpreted as having negative properties, suggesting that exotic matter might not be entirely out of reach. However, harnessing this effect on a scale large enough to stabilize a wormhole or black hole portal is a monumental challenge, one that would require technology far beyond our current capabilities. So, could exotic matter be the key to interuniversal travel? The idea is tantalizing, but it's still firmly in the realm of theory. even if exotic matter exists, producing and manipulating it would require breakthroughs in both physics and engineering. Imagine trying to bottle a substance that bends the very rules of reality. It's no small feat, yet the potential rewards are immense. If we could harness exotic matter, it might open the door to traversable wormholes, stable black hole portals, and even journeys to other universes. But let's not get ahead of ourselves. For now, exotic matter remains a fascinating concept, one that challenges our understanding of the universe and pushes the boundaries of what we think is possible. It's a reminder that the cosmos is full of surprises, waiting for us to uncover them. And while the road to discovering and utilizing exotic matter is long and uncertain, the journey itself is a testament to the boundless curiosity that drives us to explore the unknown. As we continue to probe the mysteries of exotic matter, we're not just chasing a scientific breakthrough, we're reimagining the very fabric of reality. Whether or not it holds the key to interuniversal travel, the pursuit of exotic matter invites us to dream bigger, think deeper, and explore the universe in ways we've never imagined. And who knows, the answers we find might just change everything. Imagine a universe teeming with countless stars, planets, and the potential for life, yet despite all its vastness, we've never encountered another intelligent civilization. This is the essence of the Fermi Paradox, a question that has puzzled scientists and dreamers alike. If the cosmos is so full of possibilities, where is everyone? One intriguing possibility is that advanced civilizations aren't just out there, they're beyond our reach, using black holes as gateways to traverse the multiverse. Could these cosmic giants hold the key to solving one of the greatest mysteries in science? The Fermi Paradox takes its name from physicist Enrico Fermi, who famously asked, "Where is everybody?" Given the billions of stars in our galaxy alone, many of which are older than our Sun, it seems statistically likely that intelligent life should have emerged elsewhere. And yet, we've found no evidence, no signals, no artifacts, no signs of visitation. This absence has led to countless theories, from the idea that intelligent life is rare or short-lived to the possibility that advanced civilizations might be hiding or communicating in ways we can't detect. But what if the answer lies in black holes? If black holes truly are gateways to other universes, it's possible that advanced civilizations have mastered the technology to use them for interuniversal travel. Instead of exploring our universe, they might be moving between realms, leaving little trace of their presence. This idea isn't just speculative, it's rooted in the same physics that suggests black holes could be portals. The immense gravitational forces and extreme conditions near black holes might make them the ultimate cosmic highways, accessible only to civilizations far more advanced than our own. Think about it. If a civilization could harness the energy of a black hole or navigate the complexities of its event horizon, they might bypass the limitations of space-time altogether. Instead of traveling vast distances across our universe, they could leap between universes, exploring realities beyond our imagination. This could explain why we haven't found them. They're not just elsewhere in space, they're elsewhere in the multiverse. Of course, this raises another question. Why wouldn't they leave behind some evidence of their existence? One possibility is that the process of traversing a black hole is so energy-intensive or risky that it leaves little room for communication or exploration within our universe. Alternatively, they might view our universe as just one of countless others, not worth extensive exploration or contact. It's a humbling thought, but one that aligns with the sheer scale and complexity of the multiverse hypothesis. The implications of this idea are profound. If black holes are gateways used by advanced civilizations, it could redefine our understanding of intelligent life and its place in the cosmos. It also challenges us to rethink how we search for extraterrestrial intelligence. Instead of looking for signals or spacecraft, we might need to focus on the subtle signs of black hole manipulation or the faint traces of energy that could hint at interuniversal travel. As we grapple with the Fermi Paradox, we're reminded that the universe is full of mysteries waiting to be solved. Black holes, with their immense power and enigmatic nature, might hold the key to answering one of our most profound questions. Whether they are gateways to other universes or simply cosmic enigmas, they challenge us to think bigger, explore deeper, and imagine a cosmos far more interconnected and far more mysterious than we ever dreamed. So, the next time you gaze at the night sky, ponder this. The silence we hear might not be an absence of life, but a sign that the universe is far more vast and complex than we can comprehend. And who knows, the answers we seek might not be in the stars above, but in the black holes that lie between them. When two black holes collide, the universe doesn't just take notice, it shudders. These cosmic events send ripples through the fabric of space-time, known as gravitational waves, which were first detected in 2015 by the LIGO Observatory. But what if these monumental collisions do more than just shake the cosmos? What if they could tear open temporary gateways to other universes? Let's dive into the fascinating dynamics of black hole mergers and explore whether these cataclysmic events might hold the key to unlocking interuniversal portals. Black hole mergers are some of the most energetic events in the universe. When two black holes spiral toward each other, their immense gravitational fields distort space-time, creating waves that propagate across the cosmos at the speed of light. These gravitational waves carry information about the black hole's masses, spins, and the violence of their collision. But they might also carry something else, the potential to momentarily warp space-time in ways that could create a bridge to another reality. The idea hinges on the extreme conditions generated during a merger. As the black holes orbit each other, they create a swirling vortex of gravitational energy, stretching and twisting space-time to its limits. At the moment of collision, the combined energy is so immense that it could theoretically create a temporary rupture in the fabric of reality. This rupture, some theorists suggest, might act as a short-lived gateway, a cosmic window to another universe. But how plausible is this idea? While the math behind gravitational waves is well understood, the physics of what happens during the merger itself is far more mysterious. The intense gravitational forces could create conditions where the laws of physics as we know them break down, potentially opening the door, quite literally, to other dimensions or universes. It's a concept that's still in the realm of speculation, but one that's grounded in the same principles that govern black holes and space-time. One intriguing possibility is that these temporary portals could be linked to wormholes. Some models suggest that the energy released during a merger could create a stable enough distortion in space-time to form a wormhole, even if only for a fraction of a second. While this might not be enough time for anything or anyone to travel through, it raises the possibility that black hole mergers could be testing grounds for the physics of interuniversal travel. Of course, there are significant challenges to this idea. The sheer violence of a black hole merger makes it an incredibly hostile environment. The gravitational tides alone would rip apart anything nearby, and the intense radiation emitted during the collision would make it nearly impossible to approach. Even if a portal were to form, surviving the journey would be a monumental task. Yet, the idea of black hole mergers as gateways to other realities is a reminder of how much we still have to learn about the universe. These cosmic collisions aren't just spectacular events, they're windows into the most extreme and mysterious aspects of physics. They challenge us to think beyond the limits of our current understanding and imagine a cosmos where the impossible might just be possible. As we continue to study black hole mergers and the gravitational waves they produce, we're not just uncovering the secrets of these cosmic giants, we're exploring the very fabric of reality itself. Whether or not they serve as gateways to other universes, black hole mergers remind us that the universe is full of surprises waiting for us to uncover them. And who knows, the answers we find might just change everything we thought we knew about the cosmos. Quantum entanglement is one of the most baffling and fascinating phenomena in physics. It's the idea that two particles, no matter how far apart they are, can be deeply connected in such a way that the state of one instantly influences the state of the other. It's as if the universe has an invisible thread tying these particles together, allowing them to communicate faster than the speed of light. But what does this strange quantum behavior have to do with black holes, and could it hold the key to understanding their potential as interuniversal portals? To explore this, let's start with the basics of entanglement. Imagine two particles created together, their properties linked in a way that defies classical physics. If you measure one particle and find it spinning clockwise, the other will instantly spin counterclockwise, no matter how far apart they are. This connection isn't just theoretical, it's been experimentally verified time and time again. But here's the twist: entanglement doesn't just happen between particles in our universe. Some scientists believe it could also occur across the boundaries of space-time itself, linking particles in one universe to those in another. Now let's bring black holes into the picture. When matter falls into a black hole, it doesn't just disappear, at least not entirely. Quantum mechanics tells us that information can't be destroyed, so something must happen to the particles that cross the event horizon. One possibility is that these particles remain entangled with their counterparts outside the black hole, creating a kind of quantum bridge between the inside and the outside. This idea, sometimes called entanglement entropy, suggests that black holes might not be the cosmic dead ends we once thought. Instead, they could be intricate systems that preserve and transmit information in ways we're only beginning to understand. But could this quantum bridge extend beyond our universe? Some theorists propose that entanglement could create connections not just within our universe but between universes. Picture this: particles inside a black hole remain entangled with particles in another universe, creating a pathway that defies our classical understanding of space and time. It's a concept that feels more like science fiction than science, but it's grounded in the same principles that govern quantum mechanics and black hole physics. Of course, there are challenges to this idea. For one, we don't yet know how to test it experimentally. The extreme conditions near a black hole make it nearly impossible to observe what's happening at the quantum level. And even if entanglement does create a bridge between universes, the question remains, could anything or anyone actually traverse it? Still, the idea of quantum entanglement as a cosmic connector is a tantalizing one. It suggests that black holes might not just be gateways to other realms, they could be quantum crossroads, linking universes through the strange and mysterious language of entanglement. This connection between quantum mechanics and black holes doesn't just deepen our understanding of these cosmic phenomena. It opens up entirely new possibilities for how we think about the multiverse and our place within it. As we explore the role of quantum entanglement in black holes, we're reminded that the universe is far stranger and more interconnected than we ever imagined. Whether entanglement holds the key to interuniversal travel or simply deepens the mystery of black holes, it's a concept that challenges us to think beyond the limits of our current knowledge and imagine a cosmos where the impossible might just be possible. So, the next time you hear about quantum entanglement, don't just think of it as a quirk of physics, think of it as a cosmic thread, weaving together the fabric of reality in ways we're only beginning to unravel. What if the fabric of space-time itself has flaws, tiny, thread-like imperfections that could hold the key to unlocking the mysteries of the multiverse? Enter cosmic strings, hypothetical one-dimensional defects that might have formed in the early universe, moments after the Big Bang. these cosmic threads, if they exist, could be the missing link in our understanding of black holes and their potential as gateways to other universes. Cosmic strings are a fascinating concept born out of the same physics that described the early universe. Picture the cosmos in its infancy, a seething, chaotic expanse of energy and matter. As the universe expanded and cooled, certain regions might have undergone phase transitions, much like water freezing into ice. During these transitions, imperfections could have formed, one-dimensional cracks in the fabric of space-time. These cracks or cosmic strings would be incredibly thin but unimaginably dense, carrying immense amounts of energy. Now, here's where it gets interesting. Some theories suggest that cosmic strings could interact with black holes, creating bridges between them or even linking different universes. Imagine a black hole connected to another by a cosmic string, like beads on a cosmic necklace. These strings could act as conduits, channeling energy or information across vast distances, or even between entirely different realms of existence. It's a concept that sounds like science fiction, but it's rooted in the same mathematics that describe the early universe and the behavior of space-time. But how could cosmic strings play a role in creating interuniversal portals? One possibility is that the immense tension and energy within a cosmic string could warp space-time in ways that open pathways to other dimensions. Picture a cosmic string passing through a black hole, twisting and stretching the fabric of reality until a temporary gateway forms. This gateway might not last long, but it could be enough to allow matter, energy, or even information to traverse between universes. Another intriguing idea is that cosmic strings could act as cosmic zippers, stitching together different regions of space-time. If a string were to connect two black holes in different universes, it might create a stable pathway between them, allowing for interuniversal travel. Of course, this is all highly speculative, but it's a concept that pushes the boundaries of our imagination and challenges us to think beyond the limits of our current understanding. The study of cosmic strings isn't just about black holes or interuniversal travel, it's about exploring the very fabric of reality. These hypothetical defects could offer clues about the early universe, the nature of space-time, and the forces that shape the cosmos. While we've yet to detect a cosmic string, their potential existence reminds us that the universe is full of surprises, waiting for us to uncover them. As we delve into the mysteries of cosmic strings, we're reminded that the cosmos is far more intricate and interconnected than we ever imagined. Whether they're threading black holes together or stitching universes into a multiverse, cosmic strings challenge us to dream bigger and explore deeper. And who knows, the answers we find might just reveal a universe or multiverse that's far more extraordinary than we ever dreamed. So, as we ponder the role of cosmic strings in the grand cosmic tapestry, let's keep an open mind. These tiny, hypothetical threads might just hold the key to unlocking some of the universe's greatest mysteries, and perhaps even the secrets of interuniversal travel itself. The spin of a black hole isn't just a fascinating detail, it's a game changer. Unlike their static, non-rotating counterparts, spinning black holes known as Kerr black holes create a dynamic and complex environment that could hold the key to their potential as interuniversal portals. But how exactly does a black hole's rotation shape its structure, and could this spin make it a more viable gateway to other realms? Let's dive into the whirlpool of possibilities. When a black hole rotates, it doesn't just sit idly in space, it drags the fabric of space-time along with it, a phenomenon known as frame dragging. Picture a spinning top submerged in honey. As it turns, it pulls the surrounding honey into a swirling motion. In the same way, a spinning black hole twists space-time around it, creating a swirling vortex that affects everything nearby. This twisting effect isn't just a cosmic curiosity. It fundamentally alters the behavior of matter and energy near the black hole, opening up intriguing possibilities. One of the most dramatic consequences of black hole spin is the creation of the ergosphere, a region outside the event horizon where space-time is dragged so forcefully that nothing can remain stationary. Within this zone, particles and even light are forced to move in the direction of the black hole's rotation. This intense drag could, in theory, provide a mechanism for extracting energy from the black hole, a process known as the Penrose mechanism. But beyond energy extraction, the ergosphere might also play a crucial role in shaping the black hole's potential as a gateway. The faster a black hole spins, the more extreme these effects become. Rapidly rotating black holes stretch and twist space-time to its limits, potentially creating conditions where the fabric of reality could tear or warp in ways that allow for interuniversal connections. Imagine a black hole spinning so fast that its immense rotational energy distorts space-time into a funnel-like shape, opening a temporary passage to another universe. This isn't just science fiction, it's a concept grounded in the mathematics of general relativity. But how plausible is this idea? While the math supports the possibility, the practical challenges are immense. The extreme gravitational forces near a rapidly spinning black hole would make traversing such a portal incredibly dangerous, if not impossible. Yet, for civilizations far more advanced than ours, the energy and technology required might not be out of reach. The spin of a black hole could provide the necessary conditions to stabilize a wormhole or create a temporary rift in space-time, offering a pathway to another universe. Another intriguing angle is the role of black hole spin in the formation of accretion disks. These glowing rings of gas and dust, heated to incredible temperatures as they spiral into the black hole, are shaped heavily by the black hole's rotation. A rapidly spinning black hole can create a more energetic and turbulent accretion disk, potentially generating the immense energy needed to sustain a portal or wormhole. The interplay between spin, gravity, and energy in these systems could be the key to unlocking the secrets of interuniversal travel. Of course, many questions remain. We don't yet fully understand how black hole spin interacts with quantum mechanics or the nature of singularities. And while the idea of spinning black holes as gateways is tantalizing, it's still firmly in the realm of theory. But that's what makes this field so exciting. Every new discovery, every new insight brings us closer to understanding the true nature of these cosmic enigmas. As we continue to explore the role of black hole spin, we're reminded that the universe is full of surprises. Whether rapidly spinning black holes serve as gateways to other universes or simply deepen the mystery of these cosmic giants, they challenge us to think beyond the limits of our current knowledge and imagine a cosmos where the impossible might just be possible. So the next time you think about black holes, consider this. Their spin might not just shape their destiny, it could shape ours as well. Black holes are often thought of as purely gravitational monsters, devouring everything in their path with an irresistible pull. But there's another force at play, one that's just as powerful, though less visible: magnetic fields. These invisible lines of force, generated by the swirling motion of charged particles in the accretion disk, can reach staggering strengths near a black hole. But could these magnetic fields do more than just shape the flow of matter? Could they hold the key to stabilizing or even creating interuniversal portals? Let's dive into the electrifying world of black hole magnetism and explore how these fields might shape the destiny of cosmic gateways. Magnetic fields around black holes are no ordinary force. They're generated by the intense motion of charged particles in the accretion disk, the glowing ring of gas and dust that spirals into the black hole. As these particles whirl around at near light speeds, they create electric currents, which in turn produce magnetic fields. These fields can be so strong that they rival the black hole's gravity in shaping the behavior of nearby matter. In fact, they're often responsible for launching powerful jets of particles that shoot out from the black hole's poles at incredible speeds, extending far into space. But what does this have to do with interuniversal portals? One intriguing possibility is that magnetic fields could help stabilize the extreme conditions near a black hole's event horizon, creating the necessary environment for a gateway to form. Think of it like a cosmic scaffold. The magnetic field lines could act as a framework, holding open a potential wormhole or other cosmic shortcut long enough for matter or energy to traverse it. It's a concept that's still in the realm of theory, but one that's grounded in the physics of how magnetic fields interact with space-time. Another angle to consider is the role of magnetic reconnection, a process where magnetic field lines break and reconnect, releasing vast amounts of energy. Near a black hole, this phenomenon could create bursts of energy intense enough to warp space-time, potentially opening temporary pathways to other universes. Picture a cosmic spark igniting a brief but powerful connection between realms. While this idea is speculative, it's a reminder of how magnetic fields can influence the most extreme environments in the universe. Of course, there are challenges to this idea. The sheer strength of a black hole's magnetic field could make traversing such a portal incredibly dangerous, tearing apart anything that approaches. But for civilizations far more advanced than ours, the ability to harness and manipulate these fields might not be out of reach. Imagine a technology capable of using magnetic fields to create a stable pathway, turning the chaotic energy of a black hole into a controlled gateway. The study of magnetic fields around black holes isn't just about understanding these cosmic giants. It's about exploring the interplay of forces that shape the universe. Whether they're launching jets of particles, stabilizing wormholes, or creating bursts of energy that warp space-time, magnetic fields remind us that black holes are more than just gravitational traps. They're dynamic, electrifying systems that challenge us to think beyond the limits of our current knowledge. As we continue to unravel the mysteries of black hole magnetism, we're reminded that the universe is full of surprises. Whether magnetic fields hold the key to interuniversal travel or simply deepen the enigma of black holes, they invite us to dream bigger and explore deeper. And who knows, the answers we uncover might just reveal a cosmos far more interconnected and far more electrifying than we ever imagined. As we gaze into the swirling chaos surrounding a black hole, one feature stands out like a cosmic beacon: the accretion disk. This glowing ring of gas, dust, and plasma spirals inward at incredible speeds, heating up to millions of degrees and emitting torrents of radiation across the electromagnetic spectrum. But beyond their dazzling light shows, could these disks hold the key to unlocking interuniversal portals? Let's peel back the layers of these cosmic whirlpools and explore how they might power the ultimate cosmic gateways. Accretion disks are more than just stunning visual phenomena. They are powerhouses of energy. As matter spirals toward the black hole, friction and magnetic forces heat it to extreme temperatures, causing it to glow brightly and release vast amounts of energy. This energy isn't just radiated outward, it's also channeled into powerful jets that shoot out from the black hole's poles, extending thousands of light years into space. The sheer scale of this energy output is staggering, rivaling the combined luminosity of billions of stars. Now, imagine harnessing that energy. If accretion disks can generate such immense power, could they provide the fuel needed to open or sustain a portal to another universe? One intriguing possibility is that the intense radiation and magnetic fields within an accretion disk could create the conditions necessary for a wormhole or other cosmic shortcut. Picture the disk as a cosmic engine using its energy to warp space-time and create a stable pathway to another realm. It's a concept that feels straight out of science fiction, but it's grounded in the physics of these extreme environments. But how exactly could this work? One idea is that the magnetic fields generated by the swirling matter in the disk could interact with the black hole's gravity, creating ripples in space-time that open temporary gateways. Alternatively, the immense energy released by the disk could be focused and directed in ways that stabilize a wormhole, counteracting the forces that would otherwise cause it to collapse. While these ideas are still speculative, they offer a tantalizing glimpse into how accretion disks might play a pivotal role in interuniversal travel. There's also the question of scale. Supermassive black holes with their enormous accretion disks could potentially generate the energy needed for such feats. These cosmic giants found at the centers of galaxies are surrounded by disks that span billions of kilometers and emit energy on an almost unimaginable scale. If any black hole could serve as a gateway, it might be one of these supermassive behemoths powered by the sheer magnitude of their accretion disks. Of course, the challenges are immense. The extreme temperatures, intense radiation, and powerful magnetic fields near an accretion disk would make any attempt to harness its energy incredibly dangerous. Yet, for a civilization far more advanced than ours, these obstacles might not be insurmountable. Imagine a technology capable of tapping into the disk's energy, using it to unlock the secrets of space-time itself. Accretion disks are more than just cosmic spectacles. They're windows into the most energetic and dynamic processes in the universe. Whether they hold the key to interuniversal travel or simply deepen the mystery of black holes, they challenge us to think bigger and explore deeper. As we continue to study these swirling rings of light and energy, we're not just uncovering the secrets of black holes, we're exploring the very limits of what's possible in the cosmos. So, the next time you see an image of a black hole surrounded by its glowing disk, remember, this isn't just a beautiful cosmic phenomenon. It's a reminder of the universe's boundless energy and the endless possibilities it holds. Who knows, the answers we seek might just be swirling within those luminous rings, waiting for us to unlock their secrets. Quantum tunneling is one of those mind-bending phenomena that makes quantum mechanics feel like magic. Imagine a particle facing an impenetrable barrier, a wall it shouldn't be able to cross based on the laws of classical physics, yet somehow it does. It doesn't go over or around the barrier, it seemingly passes through it as if the wall doesn't exist. This isn't science fiction, it's a well-documented quantum effect that plays a crucial role in everything from nuclear fusion in stars to the functioning of modern electronics. But what if this strange behavior could extend beyond the microscopic world? What if quantum tunneling could enable travel through the most extreme environments in the universe, like black holes? At its core, quantum tunneling occurs because particles don't behave like solid objects. Instead, they exist as probabilities described by wave functions that can extend beyond physical barriers. In simple terms, there's always a small but non-zero chance that a particle will tunnel through a barrier, even if it doesn't have enough energy to overcome it classically. It's like rolling a ball up a hill and watching it vanish halfway, only to reappear on the other side. Now, let's apply this idea to black holes. At the event horizon, the gravitational pull is so intense that nothing, not even light, can escape. But what if quantum tunneling could provide a way out or a way through? Some theorists suggest that particles near the event horizon might exploit this effect, tunneling through the barrier of space-time itself and emerging on the other side. This could mean that black holes aren't the ultimate cosmic dead ends we once thought. Instead, they might be riddled with quantum backdoors, offering a potential pathway to other regions of space-time or even other universes. But how plausible is this idea? While quantum tunneling is a well-established phenomenon, applying it to something as extreme as a black hole is a leap. The event horizon isn't just a simple barrier, it's a region where the laws of physics as we know them break down. the intense gravitational forces and warped space-time could make tunneling far more complex, if not impossible, on a macroscopic scale. Yet, the math doesn't entirely rule it out. Some models suggest that quantum effects near the event horizon could create fleeting pathways, allowing particles, or even information, to escape or traverse the black hole. One intriguing possibility is that quantum tunneling could work in tandem with other phenomena, like wormholes or entanglement, to create stable interuniversal pathways. Picture this: a particle tunnels through the event horizon, creating a temporary connection to another region of space-time. While this might only last for an instant, it could be enough to open a doorway to another universe. It's a concept that pushes the boundaries of what we thought was possible, but it's grounded in the same quantum principles that govern the behavior of particles at the smallest scales. Of course, there's a catch. Even if quantum tunneling could create a pathway through a black hole, surviving the journey would be another matter entirely. The tidal forces near the event horizon are so extreme that anything, or anyone approaching it, would be torn apart long before tunneling could occur. But for a civilization far more advanced than ours, the ability to harness or manipulate quantum tunneling might not be out of reach. Imagine technology capable of stabilizing these fleeting pathways, turning a black hole's quantum quirks into a cosmic highway. Quantum tunneling reminds us that the universe operates by rules that often defy our intuition. It challenges us to think beyond the limits of classical physics and explore the strange, counterintuitive world of quantum mechanics. Whether it holds the key to interuniversal travel or simply deepens the mystery of black holes, it's a concept that invites us to dream bigger and explore deeper. As we continue to unravel the mysteries of quantum tunneling, we're reminded that the cosmos is full of surprises. Whether it's a particle slipping through an impenetrable barrier or a black hole offering a fleeting glimpse of another universe, the possibilities are as vast as the universe itself. And who knows, the answers we seek might just be hiding in the quantum shadows, waiting for us to uncover them. Black holes aren't eternal cosmic giants, they have a lifespan, and it's a surprisingly fragile one. Over unimaginably long timescales, black holes slowly lose mass through a process known as Hawking radiation, a phenomenon predicted by physicist Stephen Hawking in the 1970s. This gradual evaporation means that even the mightiest black holes will one day fade away, leaving behind a faint whisper of their former selves. But here's where it gets fascinating. As black holes evaporate, could they also create fleeting opportunities for interuniversal travel? Let's dive into the science of black hole evaporation and explore whether this process might hold the key to unlocking cosmic gateways. Hawking radiation occurs because of the strange behavior of quantum particles near a black hole's event horizon. In the vacuum of space, pairs of particles and antiparticles constantly pop into existence, only to annihilate each other almost instantly. But near the event horizon, something extraordinary happens. If one particle falls into the black hole while its partner escapes, the black hole loses a tiny amount of energy. Over time, this process causes the black hole to shrink, emitting radiation as it does so. It's like watching a cosmic iceberg slowly melt, releasing energy into the void. Now consider what happens as a black hole evaporates. As it loses mass, its gravitational pull weakens and its event horizon shrinks. At some point, the black hole's mass becomes so small that the radiation it emits becomes more intense, accelerating its evaporation. In the final moments of its existence, the black hole releases a burst of energy, a cosmic flash that signals its demise. But could this final burst of radiation do more than just mark the end of a black hole's life? Some theorists suggest it might create a temporary disturbance in space-time, opening a fleeting pathway to another universe. The idea hinges on the extreme conditions generated during the final stages of evaporation. As the black hole's mass approaches zero, the intense energy released could warp space-time in ways that create a brief but powerful connection to another realm. Picture it as a cosmic spark igniting a momentary bridge between universes. While this gateway might only last for an instant, it raises the tantalizing possibility that black hole evaporation could be more than just an end, it could also be a beginning. Of course, there are challenges to this idea. The energy released during evaporation is immense, but the timescales involved are incredibly short. Any gateway created would likely collapse almost immediately, making it nearly impossible to traverse. Additionally, the intense radiation and extreme conditions near an evaporating black hole would pose significant risks to anything or anyone attempting to approach it. But for civilizations far more advanced than ours, the ability to harness or stabilize these fleeting pathways might not be out of reach. Another intriguing angle is the role of quantum effects during evaporation. As a black hole shrinks, the quantum nature of space-time becomes more pronounced, potentially creating conditions where the rules of physics as we know them break down. This could open the door to phenomena like quantum tunneling or entanglement, offering new pathways for matter, energy, or even information to traverse between universes. It's a concept that pushes the boundaries of our understanding, but one that's grounded in the same principles that govern the behavior of particles at the smallest scales. Black hole evaporation reminds us that even the most powerful objects in the universe are subject to the laws of physics. It's a humbling thought, but also an inspiring one. As we continue to study this process, we're not just uncovering the secrets of black holes, we're exploring the very fabric of reality itself. Whether black hole evaporation creates opportunities for interuniversal travel or simply deepens the mystery of these cosmic giants, it challenges us to think bigger and explore deeper. So the next time you hear about Hawking radiation, don't just think of it as the end of a black hole story. Think of it as a cosmic spark, igniting possibilities we're only beginning to understand. Who knows, the answers we seek might just be hiding in the fading glow of an evaporating black hole, waiting for us to uncover them. In 2019, humanity achieved a monumental milestone, the first ever image of a black hole's shadow. Captured by the Event Horizon Telescope, this groundbreaking snapshot revealed the silhouette of the supermassive black hole at the heart of the galaxy Messier 87. The glowing ring of light surrounding the dark void wasn't just a stunning visual, it was a window into the extreme physics at play near a black hole. But what if this shadow could do more than just confirm Einstein's predictions? What if it holds clues about whether black holes could serve as gateways to other universes? A black hole's shadow isn't just an absence of light, it's a complex interplay of gravity, light, and space-time. The dark center represents the event horizon, the point of no return where light can't escape. Surrounding it is the bright ring, formed by light bending around the black hole's immense gravitational field. This bending, known as gravitational lensing, creates a distorted image that reveals critical details about the black hole's structure, such as its size, spin, and the shape of its event horizon. But beyond these insights, could the shadow also hint at the presence of phenomena like wormholes or other cosmic pathways? One intriguing possibility is that the shadow's structure could reveal distortions in space-time caused by extreme gravitational effects. If a black hole were acting as a gateway, the intense warping of space-time near its event horizon might leave subtle imprints on the shadow. For example, a rapidly spinning black hole could create asymmetries or irregularities in the shadow's shape, potentially indicating the presence of a stable wormhole or other exotic features. While we haven't yet observed such anomalies, the data from the Event Horizon Telescope is still being analyzed, leaving room for exciting discoveries. Another angle to consider is the role of the accretion disk in shaping the shadow. The glowing ring of light in the image comes from the superheated gas and dust swirling around the black hole. If this material were funneled into a wormhole or other cosmic pathway, it could create unique patterns in the shadow's structure. Imagine a faint secondary ring or a distortion in the light curve, subtle signs that the black hole isn't just a cosmic vacuum but a dynamic system with hidden connections to other realms. Of course, interpreting these signals is no easy task. The extreme conditions near a black hole make it difficult to distinguish between ordinary gravitational effects and signs of something more extraordinary. Yet, the very existence of black hole shadows gives us a powerful tool for probing these mysteries. By studying their shapes, brightness, and variations, scientists can test theories about the nature of black holes and their potential as interuniversal portals. The first image of a black hole's shadow was a triumph of human ingenuity, but it was also a starting point. It reminded us that even the darkest corners of the universe can shed light on the most profound questions. Whether black hole shadows hold the key to unlocking cosmic gateways or simply deepen the mystery of these enigmatic objects, they challenge us to think bigger and explore deeper. So, as we continue to analyze these cosmic silhouettes, let's keep an open mind. The answers we seek might not just lie in the light we see, but in the shadows we've only just begun to understand. And who knows, the next breakthrough could come from a single, flickering image, revealing a universe far more interconnected than we ever imagined. Black holes aren't just gravitational powerhouses, they're also cosmic thermostats. That's right, these enigmatic objects have temperature and entropy, properties that tie them directly to the laws of thermodynamics. But what does that mean for their potential as gateways to other universes? Let's take a closer look at the thermodynamics of black holes and explore how these fundamental properties might shape their role in the cosmos. At first glance, the idea of a black hole having temperature seems counterintuitive. After all, these objects are known for their ability to swallow light and matter, not radiate heat. But thanks to Stephen Hawking's groundbreaking work, we now know that black holes emit a faint glow of radiation known as Hawking radiation. This radiation isn't just a byproduct, it's a direct result of the black hole's temperature, which is inversely proportional to its mass. Smaller black holes are hotter, emitting more radiation, while larger ones are cooler and radiate less. Entropy, on the other hand, is a measure of disorder or randomness in a system. For black holes, entropy is directly tied to the surface area of their event horizons. The larger the event horizon, the higher the entropy, meaning the black hole contains more information about the matter and energy it has consumed. This connection between entropy and surface area is a cornerstone of black hole thermodynamics and hints at a deeper relationship between gravity, quantum mechanics, and the fundamental laws of physics. Now here's where it gets fascinating. If black holes have temperature and entropy, could these properties influence their ability to act as gateways? One intriguing possibility is that the thermodynamic behavior of a black hole could create conditions where space-time becomes more malleable, opening the door to interuniversal pathways. Picture this: as a black hole radiates energy and loses mass, its temperature increases and its entropy changes. These fluctuations could destabilize the fabric of space-time just enough to create a temporary connection to another universe. Another angle to consider is the role of entropy in preserving information. If black holes encode information on their event horizons, as the holographic principle suggests, this information could play a key role in stabilizing any potential gateway. Think of entropy as a cosmic glue, holding together the delicate balance needed for a portal to form. Without it, the extreme conditions near a black hole might tear apart any pathway before it could be used. Of course, these ideas are still in the realm of theory. The thermodynamics of black holes is a complex field, and we're only beginning to understand how these properties interact with the broader laws of physics. But that's what makes this area of study so exciting. Every new discovery, every new insight brings us closer to understanding whether black holes could truly serve as interuniversal portals. As we explore the thermodynamics of black holes, we're reminded that these cosmic giants are more than just gravitational traps. They're dynamic systems governed by the same fundamental laws that shape the rest of the universe. Whether their temperature and entropy hold the key to unlocking cosmic gateways or simply deepen the mystery of these enigmatic objects, they challenge us to think bigger and explore deeper. So, the next time you hear about Hawking radiation or black hole entropy, don't just think of them as abstract concepts. Think of them as clues hidden within the fabric of space-time, waiting to reveal the universe's most profound secrets. Who knows, the answers we seek might just be encoded in the thermodynamics of black holes, waiting for us to uncover them. Black holes are often thought of as cosmic vacuums, swallowing everything in their path and leaving no trace behind. But what if they're not just destroyers of information? What if they're also cosmic librarians, meticulously storing every detail of the matter they consume? This idea, rooted in the holographic principle, suggests that the event horizon of a black hole isn't just a boundary, it's a vast two-dimensional data storage system. But here's the twist: if black holes can store information, could we one day decode it? And more intriguingly, could this stored data help us navigate potential interuniversal portals? The holographic principle is a mind-bending concept that emerged from the intersection of quantum mechanics and general relativity. It proposes that all the information about the three-dimensional space inside a black hole can be encoded on its two-dimensional event horizon. Picture a hologram, a flat surface that, when illuminated, creates the illusion of depth. In the same way, the event horizon of a black hole might contain a complete blueprint of everything that has fallen into it. This isn't just a metaphor, it's a mathematical reality, supported by equations that describe the way black holes interact with space-time and quantum fields. So, how does this stored information work? Imagine every particle, every atom, and every bit of energy that crosses the event horizon leaves an imprint, like a cosmic fingerprint etched onto the surface. These imprints aren't random, they're precise, encoding the properties and history of the objects that entered the black hole. This means that, in theory, the information isn't lost, it's transformed into a form we don't yet fully understand. But if we could decode this data, it might offer unprecedented insights into the nature of black holes and their potential as gateways. Now, let's take this a step further. If the event horizon stores information, could this data be used to navigate a black hole's interior, or even a pathway to another universe? One possibility is that the encoded information could act as a kind of cosmic map, guiding travelers through the extreme conditions near the event horizon. Picture this: a spacecraft equipped with technology capable of reading the holographic data stored on the event horizon, using it to chart a safe course through the black hole's gravitational maelstrom. It's a concept that feels straight out of science fiction, but it's grounded in the same physics that describes black hole information storage. Another intriguing angle is the role of quantum entanglement in this process. If particles falling into a black hole remain entangled with those outside, the information on the event horizon could serve as a bridge, connecting the inside and outside of the black hole in ways that defy classical physics. This entangled data might not just preserve information, it could also create a pathway for it to escape or traverse the black hole, offering a potential mechanism for interuniversal communication or travel. Of course, decoding and utilizing this information is no small feat. The extreme conditions near a black hole make it nearly impossible to approach, let alone extract data from. But for a civilization far more advanced than ours, the ability to harness this stored information might not be out of reach. Imagine technology capable of reading the holographic code of a black hole, unlocking its secrets and perhaps even revealing the pathways to other universes. The idea of black holes as information storage systems challenges us to rethink their role in the cosmos. They're not just gravitational traps, they're intricate, dynamic systems that preserve and process information in ways we're only beginning to understand. Whether this stored data holds the key to unlocking interuniversal portals or simply deepens the mystery of black holes, it's a concept that pushes the boundaries of our imagination. As we continue to explore the role of black hole information storage, we're reminded that the universe is far more complex and far more interconnected than we ever imagined. The answers we seek might not just be hidden within the depths of a black hole, they could be encoded on its surface, waiting for us to uncover them, and who knows? The next breakthrough might just come from decoding the cosmic library of a black hole's event horizon, revealing a universe or multiverse far more extraordinary than we ever dreamed. When two black holes collide, the universe doesn't just witness a cosmic event, it feels it. These titanic mergers send ripples through the fabric of space-time, known as gravitational waves, which we've only recently begun to detect. But what if these collisions do more than just shake the cosmos? What if they could tear open temporary gateways to other universes? Let's explore the incredible dynamics of black hole collisions and whether these cataclysmic events might hold the key to unlocking interuniversal portals. The moment two black holes spiral toward each other, space-time itself becomes a stage for one of the universe's most dramatic performances. As they orbit closer and closer, their immense gravitational fields distort the surrounding space, creating waves that ripple outward at the speed of light. When they finally merge, the energy released is staggering, equivalent to converting several times the mass of the Sun into pure gravitational waves in a fraction of a second. It's a display of cosmic power unlike anything else in the universe, but here's where it gets truly fascinating. During the collision, the intense gravitational forces could warp space-time to such an extreme degree that they create a temporary rupture, a fleeting moment where the fabric of reality might open a doorway to another universe. Picture the collision as a cosmic hammer striking space-time, creating a crack that leads to an entirely different realm. While this idea is still speculative, it's grounded in the same physics that describe black holes and the curvature of space-time. One intriguing possibility is that these collisions could generate wormholes, hypothetical tunnels through space-time that connect distant regions or even different universes. The immense energy released during a merger might be enough to stabilize a wormhole, even if only for an instant. While this wouldn't provide a practical pathway for travel, it raises the tantalizing question of whether black hole collisions could serve as testing grounds for the physics of interuniversal connections. Another angle to consider is the role of the newly formed black hole after the collision. The resulting object, often spinning rapidly and surrounded by a turbulent accretion disk, could create an environment ripe for extreme space-time distortions. If a wormhole or other cosmic pathway were to form, it might be anchored by the intense gravitational and rotational forces of this newly born black hole. It's a concept that pushes the boundaries of our imagination, but one that aligns with the extreme physics of these cosmic events. Of course, there are significant challenges to this idea. The sheer violence of a black hole collision makes it an incredibly hostile environment. The gravitational tides alone would tear apart anything nearby, and the intense radiation emitted during the merger would make it nearly impossible to approach. Even if a portal were to form, surviving the journey would be a monumental task. Yet, the idea of black hole collisions as gateways to other realities is a reminder of how much we still have to learn about the universe. These cosmic mergers aren't just spectacular events, they're windows into the most extreme and mysterious aspects of physics. They challenge us to think beyond the limits of our current understanding and imagine a cosmos where the impossible might just be possible. As we continue to study black hole collisions and the gravitational waves they produce, we're not just uncovering the secrets of these cosmic giants, we're exploring the very fabric of reality itself. Whether these collisions create fleeting gateways or simply deepen the mystery of black holes, they remind us that the universe is full of surprises waiting for us to uncover them. So the next time you hear about a black hole collision, don't just think of it as a cosmic spectacle. Think of it as a cosmic hammer, striking the anvil of space-time and forging possibilities we're only beginning to imagine. Who knows, the answers we seek might just be hidden in the echoes of these monumental events. Black hole jets are among the most dramatic and awe-inspiring phenomena in the universe. Picture streams of particles accelerated to nearly the speed of light, shooting out from the poles of a black hole and extending thousands, sometimes even millions of light years into space. These jets are so powerful that they can outshine entire galaxies, carving out vast regions of space and shaping the cosmic landscape around them. But could these colossal fountains of energy hold a deeper secret? Could they be connected to the tantalizing possibility of interuniversal portals? To understand black hole jets, we need to look at the forces that drive them. These jets are born from the swirling chaos of the accretion disk, the superheated ring of gas and dust that spirals into a black hole. As matter falls inward, it generates immense magnetic fields which twist and coil like cosmic springs. These magnetic fields, combined with the black hole's rotation, act like a particle accelerator, launching jets of charged particles into space at incredible speeds. The result is a cosmic firehose of energy capable of influencing entire galaxies and even the intergalactic medium. Now, here's where it gets intriguing. Some theorists suggest that these jets might do more than just spew energy into the void. They could also play a role in creating or stabilizing pathways to other universes. Imagine the immense power of a black hole jet being harnessed to warp space-time, opening a temporary gateway to another realm. The energy and magnetic forces within these jets could, in theory, create conditions where space-time becomes flexible enough to form a bridge between universes. It's a concept that feels like science fiction, but it's grounded in the same physics that describes how black holes and their jets interact with the fabric of reality. But how plausible is this idea? While black hole jets are undeniably powerful, the mechanisms needed to transform them into interuniversal gateways are still speculative. The extreme conditions near the base of a jet, intense radiation, powerful magnetic fields, and gravitational forces would make any attempt to approach or manipulate them incredibly dangerous. Yet, for civilizations far more advanced than ours, the ability to harness this energy might not be out of reach. Imagine a technology capable of channeling the raw power of a black hole jet, using it to create a stable pathway to another universe. Another angle to consider is the role of magnetic reconnection, a process where magnetic field lines break and reconnect, releasing bursts of energy. Near the base of a black hole jet, this phenomenon could create localized distortions in space-time, potentially opening temporary portals. While these gateways might only last for an instant, they could provide a glimpse into the mechanics of interuniversal travel. It's a tantalizing possibility, but one that pushes the boundaries of our current understanding. Black hole jets remind us that the universe is full of surprises. These colossal streams of energy aren't just cosmic spectacles, they're windows into the most extreme and dynamic processes in the cosmos. Whether they hold the key to unlocking interuniversal portals or simply deepen the mystery of black holes, they challenge us to think bigger and explore deeper. So, the next time you see an image of a black hole jet stretching across the cosmos, remember, this isn't just a beautiful display of cosmic power. It's a reminder that the universe is far more interconnected and far more mysterious than we ever imagined. And who knows, the answers we seek might just be hidden in the fiery beams of these cosmic fountains, waiting for us to uncover them. Black holes are often thought of as the ultimate cosmic vacuum cleaners, devouring everything in their path. But beneath their immense gravitational pull lies a hidden layer of complexity, entropy. This concept, often described as a measure of disorder, plays a crucial role in understanding black holes, and it might even hold the key to unlocking their potential as interuniversal portals. Let's dive into the fascinating world of black hole entropy and explore how this seemingly abstract idea could reshape our understanding of the cosmos. At its core, entropy is a way of quantifying the amount of disorder or randomness in a system. For black holes, entropy is directly tied to the surface area of their event horizons. The larger the event horizon, the higher the entropy, meaning the black hole contains more information about the matter and energy it has consumed. This connection between entropy and surface area is more than just a curious detail. It's a cornerstone of black hole thermodynamics and hints at a deeper relationship between gravity, quantum mechanics, and the fundamental laws of physics. Now, here's where it gets intriguing. If black holes encode information on their event horizons, as the holographic principle suggests, could this entropy play a role in stabilizing or even creating interuniversal portals? One possibility is that the immense entropy of a black hole could act as a kind of cosmic glue, holding open a potential wormhole or other cosmic shortcut. Imagine entropy as the balancing force that counteracts the extreme gravitational forces near a black hole, creating the conditions needed for a gateway to form. But let's take this a step further. Some theories propose that black hole entropy isn't just a passive property, it could actively shape the behavior of space-time. For example, fluctuations in entropy might create temporary distortions in the fabric of reality, opening fleeting pathways to other universes. Picture a black hole as a dynamic system, constantly shifting and changing as it interacts with its environment. These fluctuations could make space-time more malleable, allowing for the formation of temporary portals that connect our universe to others. Of course, these ideas are still in the realm of theory. The connection between black hole entropy and interuniversal travel is a complex one, and we're only beginning to understand how these concepts might interact. But that's what makes this field so exciting. Every new discovery, every new insight brings us closer to understanding whether black holes could truly serve as gateways to other realms. As we explore the role of black hole entropy, we're reminded that these cosmic giants are more than just gravitational traps. They're dynamic systems governed by the same fundamental laws that shape the rest of the universe. Whether their entropy holds the key to unlocking cosmic gateways or simply deepens the mystery of these enigmatic objects, it challenges us to think bigger and explore deeper. So the next time you hear about black hole entropy, don't just think of it as an abstract concept. Think of it as a cosmic fingerprint etched into the fabric of space-time, waiting to reveal the universe's most profound secrets. Who knows, the answers we seek might just be encoded in the entropy of black holes, waiting for us to uncover them. At the smallest scales imaginable, the fabric of space-time isn't smooth and orderly. It's a turbulent, frothy mess. This chaotic structure, known as quantum foam, is a prediction of quantum mechanics, suggesting that space-time itself fluctuates wildly at distances smaller than a billionth of a meter. It's as if the universe, when viewed under an impossibly powerful microscope, resembles a bubbling sea of energy and uncertainty. But what does this strange, microscopic chaos have to do with black holes? and could it hold the key to understanding their potential as interuniversal portals? Quantum foam arises from the inherent uncertainty of quantum mechanics. At tiny scales, particles and energy flicker in and out of existence, creating a seething, dynamic environment where the very fabric of space-time is constantly shifting. These fluctuations are so small that they're impossible to observe directly, but their effects ripple through the cosmos, influencing everything from the behavior of particles to the structure of black holes. Now let's zoom in on black holes. Near the event horizon, the gravitational pull is so intense that it warps space-time to its limits. At this boundary, the quantum foam could become even more pronounced as the extreme conditions amplify the chaotic fluctuations of space-time. Some theorists suggest that this frothy, turbulent environment might create temporary bubbles or distortions in the fabric of reality, opening fleeting pathways to other universes. Picture the quantum foam as a cosmic froth, with bubbles popping and reforming in ways that could momentarily connect our universe to others. But how plausible is this idea? While quantum foam is a well-established concept in quantum mechanics, its role in black holes is still largely speculative. The extreme gravitational forces near a black hole could either suppress or amplify these fluctuations depending on the conditions. If the foam is amplified, it might create the right environment for interuniversal connections. If suppressed, it could make such pathways impossible. The truth is, we don't yet have the tools or technology to measure these effects directly, leaving the idea in the realm of theory. One intriguing possibility is that quantum foam could interact with other phenomena, like wormholes or quantum entanglement, to stabilize or create pathways between universes. Imagine the foam acting as a kind of cosmic scaffolding, supporting the delicate structure of a wormhole or other cosmic shortcut. While this remains firmly in the realm of speculation, it's a concept that pushes the boundaries of our understanding and invites us to imagine a universe far more interconnected than we ever thought possible. As we explore the role of quantum foam in black holes, we're reminded that the universe operates on scales both unimaginably large and vanishingly small. These tiny fluctuations in space-time might seem insignificant, but they could hold the key to some of the cosmos's greatest mysteries. Whether quantum foam plays a role in creating interuniversal portals or simply deepens the enigma of black holes, it challenges us to think beyond the limits of our current knowledge and explore the universe in new and exciting ways. So, as we peer into the frothy depths of quantum foam, let's keep an open mind. The answers we seek might not just be hidden in the vastness of space, they could be lurking in the tiniest, most chaotic corners of reality itself. And who knows, the next breakthrough might just come from understanding how these microscopic fluctuations shape the grand cosmic tapestry. The future of black hole research is a frontier brimming with possibilities, and as our technology evolves, so too does our ability to unlock the secrets of these cosmic enigmas. From cutting-edge telescopes to revolutionary experiments, the tools at our disposal are expanding in ways that could transform our understanding of black holes and their potential as gateways to other universes. But what lies ahead in this thrilling journey of discovery, and what unanswered questions could reshape our view of the cosmos? One of the most exciting developments on the horizon is the next generation of space-based observatories. Projects like the James Webb Space Telescope and the planned LISA mission, a space-based gravitational wave detector, promise to peer deeper into the universe than ever before. These instruments could provide unprecedented insights into the behavior of black holes, from the way they form and grow to the intricate dance of matter and energy around their event horizons. Imagine capturing real-time images of black hole collisions or observing the faint whispers of Hawking radiation. Such discoveries could bring us closer to understanding whether black holes truly serve as interuniversal portals. But it's not just about looking deeper, it's also about thinking differently. Advances in quantum computing and artificial intelligence are opening new doors for simulating the extreme conditions near black holes. These simulations could help us test theories about wormholes, singularities, and the nature of space-time itself. By recreating the physics of black holes in a virtual environment, scientists might uncover clues about how these cosmic giants could connect to other universes. It's a bit like building a cosmic laboratory where the impossible becomes possible, at least in theory. Another area of focus is the study of black hole thermodynamics and information storage. As we refine our understanding of entropy and the holographic principle, we may discover new ways to decode the information stored on black hole event horizons. Could this data hold the key to navigating a black hole's interior, or even a pathway to another universe? The answers could redefine not just our understanding of black holes, but the very nature of reality itself. Yet, for all our progress, many questions remain. How do black holes interact with dark matter and dark energy? And could these mysterious forces play a role in creating interuniversal pathways? What happens to matter and energy as they cross the event horizon? And is there any way to retrieve or decode the information they carry? These are the puzzles that drive scientists to push the boundaries of knowledge, and they're the questions that could unlock the next great cosmic revelation. As we look to the future, one thing is certain: black holes will continue to challenge and inspire us. They are not just objects of scientific curiosity, they are windows into the most profound mysteries of the universe. Whether they serve as gateways to other realms or simply deepen the enigma of space and time, they remind us that the cosmos is full of surprises waiting for us to uncover them. So, as we stand on the brink of a new era in black hole research, let's keep our eyes on the stars and our minds open to the possibilities. The next breakthrough might not just change how we see black holes, it could change how we see the universe itself. And who knows, the answers we find might just reveal a cosmos far more extraordinary and far more interconnected than we ever dreamed. Black holes are more than just cosmic oddities. They're windows into the unknown, pushing the boundaries of what we think is possible. The idea that these immense gravitational giants could serve as gateways to other universes is both exhilarating and humbling, a reminder of how much we still have to learn about the cosmos. While the science behind this possibility is still in its early stages, the theories we've explored, wormholes, quantum entanglement, singularities, and more, offer tantalizing glimpses into a universe far more interconnected and mysterious than we ever imagined. What makes this journey so extraordinary is the way it challenges our understanding of reality itself. Black holes force us to confront the limits of our knowledge, blending the laws of gravity with the strange rules of quantum mechanics. They invite us to ask questions that stretch the boundaries of human imagination. Could we one day travel through a black hole? Are there other universes waiting beyond the event horizon? And what would it mean for humanity if we could unlock these cosmic secrets? As we've seen, the answers are far from clear. The physics of black holes is complex, and many of the ideas we've discussed remain speculative. Yet, that's what makes the pursuit so exciting. Every discovery, every new piece of data brings us closer to understanding these enigmatic objects and their potential to connect us to realms beyond our own. Whether black holes are gateways, cosmic recyclers, or something entirely different, they remind us that the universe is full of surprises waiting to be uncovered. So, as we wrap up this exploration, let's take a moment to reflect on the awe-inspiring nature of black holes. They're not just objects of scientific curiosity, they're symbols of the endless possibilities that lie ahead. The study of black holes is a journey into the unknown, a testament to human curiosity and our relentless drive to understand the cosmos. And while we may not have all the answers yet, the questions themselves are a source of wonder and inspiration. Thank you for joining us on this adventure through the mysteries of black holes. If you've enjoyed this deep dive into the cosmos, don't forget to like, subscribe, and share your thoughts in the comments below. What do you think about the idea of black holes as gateways? Are there other cosmic mysteries you'd like us to explore? Let us know. We'd love to hear from you. The universe is vast, and the journey to understand it is just beginning. Together, let's keep exploring, keep questioning, and keep reaching for the stars. The next discovery could be just around the corner, and who knows, it might just change everything. See you out there.